Okay, I wanted to continue our conversation from class from Monday and complete the PowerPoint. And this is where we left off. The next thing we're going to look at is evaluating a one-sided limit using the limit laws. And so this is the function that we're studying here. And let's go ahead and take a look on a paint screen to see what exactly is going on here. So let me just switch over to that alternate screen. So what we're looking at here is this piece first, approaching the square root of x minus 3 from the left. So I'm going to write that down again just here. And we're approaching 3 from the left. Well, it may be pretty obvious to some of you that actually this curve is not defined from the left of 3. And the reasons for that are that if we take the function and we start plugging in values that are just to the left of 3, such as, well, let's just say we plug in a 2. Well, we end up with I, which is a non-real number. And if I plug in something even closer, that's also a negative. So that would be the square root of 0.5 I. Anyway, the point is that we don't get to an actual real number until we actually get to 3. But everything to the left is non-real. Therefore, this limit does not exist. However, approaching 3 from the right is not problematic because as I approach from the right, and we'll just do this one intuitively without plugging everything in, there are values that are outputs. That's a 1. You know, that's the point 4, 1. And, you know, it may not be obvious what these are, but you see them dropping, and you see that where they end is 0. And you could use limit rules or limit laws for that. Maybe we want to do the square root of the limit of x minus 3 as x approaches 3 plus. And then even further break that up into the limit of x minus the limit of 3 as x approaches 3. So that's the square root of 3 minus 3, which is a square root of 0, which is 0. So that one does exist, and that one is 0. This one does not exist. So here's the next problem on that PowerPoint, and we're being asked to find the limit of x minus 3 over x squared minus 2x. Okay, and so let's go ahead and take a look on the paint screen to see why this one might give us a problem at first and how we might resolve that. So let me go ahead and share my paint screen with you. Okay. All right, so this is the same problem on that page, and what you may notice is that if I just try to directly plug in the 2, let's see what happens. And at this point, since I'm evaluating, I don't need to add the limit piece. But what's happening here, if I just plug it in directly into the function, then I end up with -1 over 0. And so that leaves us with an indeterminate limit. That's a question mark there. So is there a way to actually arrive at an answer here? And the answer is yes, with a little bit of creative thinking. And this is how we would approach this. What I want to do is factor out an x. And that would allow me to break this up into 2 pieces. No, they're still both inside the limit. I haven't done anything that I haven't used any special tricks yet. But if I use this property, which is a product law for limits, I'm able to break this up now into 2 limits. And hopefully, working with these individually will allow me to get an L and an M and then arrive at something that is more meaningful. In other words, this is going to be x minus 3 over x. And this is going to be, we're going to find the limit of 1 over x minus 2 as x approaches 2 from the left. Now, if I simply, I could do this in steps using all the properties, but some of you may already realize that I can plug this in and end up with a 1/2. So this becomes a 1/2. Now I've got to bring my multiplication symbol down. Now the other piece may be a little trickier to see. And I think what I'll do is I'll look at a graph. And try to think about what's happening. Now we're approaching from the left. So this is 1, this is 2. So you may realize that there is an asymptote there because I can't plug in a 2. I can't plug in a 2. But what happens as I get closer to 2? So like, for example, let's suppose that I plug in a 1. So 1 over 1 minus 2 is negative 1. Okay, so here's another question. What happens if I plug in 1.5 here? So plugging in 1.5, well, 1.5 minus 2 is a negative 1/2. And 1 divided by negative 1/2 is a 2, actually. So that's 1.5, and I have a 2. Now, what happens if I plug in something even closer, like say 1 3/4? 1 3/4. So 1 3/4 minus 2 is negative 1/4, so it's actually 4. So it's going to be over here. Now, it's hard to see what the curve is over here, but it's doing something like this. And what's happening then is that this is going towards infinity. And so this is actually going towards infinity. And it doesn't matter what you multiply it by. Well, if I have a minus sign, I guess that's going to change the sign. So this is going to be a minus infinity is what we end up with. So I stopped the video and realized actually that the values that I was plugging in, I think I was doing 1 3/4, and then before that I did 1.5. I was on the right track, except that when you plug in 1.5, let's start there. 1.5, it's actually negative 2. So 1.5 is negative 2. And then 1 3/4, when you plug that in, you get a negative 4. So it's actually going in the other direction. So it's actually going towards negative infinity as opposed to what I had. So this is a negative infinity. So this is a negative infinity. So this is a positive infinity. So I realized that I needed to make that correction. All right, so the last thing I wanted to look at was the squeeze theorem. And if we look at what the squeeze theorem says, what it's telling us to do is that if you can't find the limit of the middle function, you should find the limit of two functions that it is between. Okay? And so what that means in this case that we're going to look at here in a minute is that if we're going to find the limit of x cosine x, that maybe there's two other functions that we can find the limit of easier, that go to the same place, and that'll be squeezing on the one that we're actually interested in. And so we start off with this relationship. You know what cosine looks like. It's this function that runs roughly like this. So it runs between negative 1 and 1. It's always between those two values in both directions. So this holds. Now we take that function and we multiply by the absolute value of x, knowing that cosine of x is between negative 1 and 1, and we're going to multiply absolute value of x. So we've got the absolute value of x. And what they're actually using is x cosine x here. So we've got the absolute value of x. And what they're actually using is x cosine x here. Okay, so there's an interesting question here that if we use a squeeze theorem, we're starting off with this equation up here. Where cosine of x is between negative 1 and 1, and that's obvious just by the nature of the curve, as we explained. And so let's explore this idea that if we multiply all the way through by the absolute value of x, that's not a stretch of the imagination, because all of these are positive, and so the relationship remains. The only question is that we're actually not interested in absolute value of x cosine x, but that instead we're interested in x cosine x. So let's try to understand why this relationship still holds when you have an x here. And so the first thing we'll examine briefly is, does this hold? Okay, and we don't really need to examine much when x is greater than 0, because that's the same as an absolute value of x. So we know that it holds. The question is, does this hold when x is less than 0? In other words, when this value is negative. Now we know, so in other words, we're really interested in examining this piece, which is the negative x. And, we have the picture. So, it's, if you're just using the picture, maybe you don't need to be convinced. But is there a way to be convinced? Let me see what color I can find here. Is there a way to be convinced that this piece here still remains above the absolute value of x algebraically? And I would say that the thing that convinced me was that this piece is always going to be so we already said this is going to be negative, and the cosine x is always going to be somewhere between 1 and negative 1 and 1. And anywhere in between that, it's going to be a fraction. And so if you think about it, no matter what x is, if you multiply it by a fraction, this is going to be, in terms of magnitude, less than x, because you're multiplying it by a fraction. So even if this has the magnitude of, say, let's just, I'm trying to pick a point to help us understand. So let's say the magnitude is let's say 1.5. So something like roughly there, let's just say, and this is just roughly. So it's minus absolute value of 1.5. And so it's minus, it's minus 1.5. But the magnitude of this is, well, it's way down here. Well, if you take, let me do it up here, 1.5. Now we're dealing with negatives, right? And whatever cosine x is going to be, it's going to be a fraction. Now it just so happens that for that particular value, this is also going to be, a positive fraction, but that's not as important. The fact is that if negative 1.5 times a fraction is going to be a smaller number, which is why it's over here. And that's my rationale for why that relationship holds. So I'm not going to go through all the pieces, right? Because the other thing would be to look at each of the parts of the absolute value. But that's why we're able to draw on this relationship, and then simply take the limit of the left, which is 0, the limit of the right, which is 0, and therefore conclude that the limit of the thing in the middle that you're squeezing is, they all go to 0. And for this last slide, what we're going to look at is the limit as theta approaches 0 of 1 minus cosine theta over theta. And the way we're going to approach this one, because obviously if I plug in a 0 in the denominator, this is indeterminate. So we're going to take the function, we're going to break it up into, well, we're going to actually use a trick that we used earlier, which is multiply by a conjugate. So 1 minus cosine theta, we're going to multiply by 1 plus cosine theta over 1 plus cosine theta, which obviously that is going to be 1 over 1. So we're multiplying by 1. That doesn't change anything. But of course, once we multiply this out, and of course you do first outer, inner, last, like you've done before, and you end up with 1 minus cosine theta. And then if you remember the identity, that's the same as sine squared theta. And so now we've got to contend with sine squared theta over theta. And then actually we're going to contend with sine of theta over theta. And then we're going to break up the other sign over here, and we've got 1 plus cosine theta. Now you're going to watch a video that I'm going to post, and I want you to see it's going to give you a convincing argument for why sine theta over theta as theta approaches 0. That also seems indeterminate. So there's actually quite a bit of work for us to show that the limit is 1. And the limit on this side, if you plug in a 0, then the sine of 0 is 0, and then the cosine of 0 is 1. So that's how the 0 over 2 comes up, and the final answer is 0. But it hinges on why it is that the limit of sine theta over theta is 1, and that'll help you be convinced of how we got to this 0.